All right, let's look at a couple of 2D examples with work. Now, when I say 2D, don't start thinking like all this component work and like this crazy level of vector resolution. We're not interested in that. That's just, we want to kind of scale it back. Like that level of 2D question is done. Like we've covered the grounds for that in Physics 20. We're just going to look at some simple stuff. So, there's me, as always. I'm applying a force of 250 newtons at 35.8 degrees below the horizontal on a box. So if the box gets moved a distance of 18.6 meters, determine the work done by me on the box. So just to kind of have a look, here's the box, here's me, here's my giant muscles to move said box. So the force that's being applied on this thing, it's acting down, so we're going to say it's acting down at an angle of 18.6 degrees from the horizontal. And then we're told that this thing is going to 35.8, wrong number. 35.8 degrees, and then it's going to end up moving 18.6 meters. So in terms of my vectors, this is not a free body diagram I'm drawing. Like this is my applied force, my force vector, and this is my displacement vector. And we're told that the angle between those two, or we know the angle between those two is 35.8 degrees. So when we use work equals FD cos theta, that theta represents that angle between our displacement and force vectors. So at this point, we don't have to do anything special. We have FD and we have the cosine of the angle. This is a plug and chug. So we have 250 newtons, we have a distance of 18.6 meters, and we're going to multiply that by cosine of 35.8 degrees. So we do 250 times 18.6 times cos of 35.8. So we're going to get about 3,771 joules. So last thing, let's put that in significant digits. So we want 3. So we're going to say that the work done on this thing is about 3.77 times 10 to the 3 joules. Or if you like prefixes, we could say 3.77 kilojoules. That also works. So that's a pretty common 2D question you have. And once you know the angle between your force and displacement vectors, it's really simple. Like we're not asking you to do a very complicated calculation. This next one though, this is a bit more of a challenging 2D. But it's actually not as bad as you think, and we can actually kind of simplify it a little bit. So we got two workers. They're going to each exert 1,200 newtons to move a crate along a level floor at constant velocity, as shown in the diagram. Determine the work done on the crate by each worker if it moves due east at 1.2 meters per second for a time of 3.4 seconds. Now, this thing is moving at constant velocity. So there is a force, there's applied forces by these two ropes. Now, if this thing is moving at constant velocity, there has to be a force that's opposing the motion. Most likely, that is going to be friction. Now, if we want to look at the net work on this system, the net work is going to be 0 because the net force is going to be 0. But it's not asking for net work. It's asking for the work done on the crate by each worker. So we want to find the contribution of the work because of the two workers. For this thing to move at constant velocity, there's also a negative work that's going to counteract that, but we're not interested in that piece. We are just interested in what the workers are doing. And that's why you have to be really careful with work problems. You have to see what they're specifying, what's doing the work or what the work is being done on. Now this moves at constant velocity. So the first thing we know, constant velocity. This allows us to use the equation that some of you would love to use all the time, but you can't. This allows us to use V equals d over t. Now we know the constant speed it's traveling at, the constant velocity, and we know the time. This is going to allow us to find the displacement, because this allows us to see the distance that work acts over. So we know d is equal to vt, so we have that v of 1.2 meters per second, and then we have that 3.4 seconds. So we're going to get about 4.08 meters. So that is the distance the work is going to act over. Now we also know that work is equal to FD cos theta. Now we might start to have a little bit of a problem because we see that there's angles in here. I assure you this question's not as bad as you think. Now let's cut through the horizontal here. So we're going to have this horizontal line here. Now, what that tells us, if we know this whole angle here is 54 degrees, that is going to tell us that this angle here is 27 degrees. This angle here is 27 degrees. So both forces have equal magnitudes and they have equal angles off of the horizontal. This is actually going to make our life quite a bit easier. Because if I look at the vector diagrams for these two things, like for example, if I look at the first force up top, and then I look at the second force on the bottom here, so I'm just trying to sketch these as best I can. So this is going to have an x component, this is going to have an x component, this is going to have a y component, and this is going to have a y component. Now, because these are the exact same vectors, magnitude-wise, the components are going to be equal. But what you should notice is, yes, both x components are pointing in the same direction, and they're both the same size, so that simplifies the work. But you should notice that these y components, they are going to have the same length, but they are pointing in opposite directions. So the y components actually cancel. What that means for us is we don't actually have to consider the y direction at all. We can ignore it safely because they're going to cancel out. Once we know the component of the force in the x direction, well, that pretty much makes our life a lot easier. And that's what this equation here is for. This FD cos theta, this gives the x component, or rather the component of the force along the line of the displacement, because the displacement is in the x direction. So this force, or this component of force, this is going to give us the component of force in the x direction as well. Now, if I use this, this is just going to give me the work done for one person. So if I look for one worker, they're applying a force of 1200 newtons over a distance of 4.08 meters, and then they have that angle of 27 degrees. So that's what we have going on there. So I'm going to get about 4,362.4 joules. But that's for one worker. We know that the total work done, there's going to be the piece from the one worker and the piece from the second worker, but the two pieces are identical. So all I have to do is actually add another piece like this, or I could just double this. So total is going to be that 4,362.4 joules, and we're going to multiply it by 2 since there are two workers. So what this is going to do is this is going to give me the total work of about 8,724 joules, or 25 joules. Now I only have two significant digits, so I need to write this as about 8.7 times 10 to the 3 joules. Or I could write 8.7 kilojoules. Now, that is the work done by both of the workers on this box. Because this moves at constant velocity, that tells us the net force is 0 and the net work would be 0. So if that's the work done applied on the box, this also tells us, because of constant velocity, there's a work of negative 8.7 times 10 to the 3 joules being done by the box on the surroundings. Most likely that's going to be due to friction. So the work due to friction is going to be about negative 8.7 times 10 to the 3 joules. The big advice with work, make sure you read the problem, see what the work is being done on or what the work is being done by. That's my biggest piece of advice.